For the longest time, string theory was this beautiful but kind of abstract idea, a theory of everything that was mostly just theory. So, how do you get a real, actual, concrete answer out of it? Well, today we're going to dive into the story of string theory's very first calculation, a result so profound it changed absolutely everything.
It all kicks off with what sounds like a simple question. If the universe is really made of these tiny, vibrating strings, what actually happens when they interact? I mean, do they just bounce off each other like little billiard balls? Do they shatter into pieces? This was the first giant puzzle that physicists had to figure out. And the answer they found? Well, it's so much more elegant than a simple crash. See, a string interaction isn't just a single event happening at one point in time. Instead, as these strings move and merge and split, they actually trace out a continuous surface through space-time. It's less of a collision and more like a beautifully choreographed performance. Okay, so to calculate the outcome of this incredible dance, physicists first had to define this stage where it all happens. And in the language of string theory, this cosmic stage has a name, the world sheet. The world sheet is, and this is crucial, the fundamental canvas for everything that happens. It's this special mathematical surface where every single twist, every merger, every split of the strings is perfectly recorded. You can think of it as the complete blueprint of the entire interaction, from the very beginning to the very end. So, how do we pick the right stage for our performance? Well, it turns out the type of string we're dealing with actually dictates the shape of the world sheet itself. We've got two main characters in this cosmic play. First up, you have your closed strings. These are complete loops, right? When they interact, their world sheet is a totally seamless surface with no edges, no boundaries, basically a sphere. Then you've got open strings, which, as the name suggests, have two distinct endpoints. Their world sheet is a surface with a boundary, kind of like a flat desk. And here you can see what we're talking about. These are the actual diagrams physicists use. Don't worry about the equations, just look at the shapes. Over on the left, for the closed strings, you can see that smooth, seamless sphere. But on the right, for the open strings, it's a disk. And that boundary, that edge, is the key difference. That's where the endpoints of the open strings live and trace their paths. Okay, so we've got our stage. Now, how do we actually write the script? How do we figure out the probability of a certain outcome? For that, we need a very special set of mathematical tools.
Let's talk about the vertex operator. The easiest way to think about these is as little pins that you stick into the world sheet. Each pin represents one string with a specific energy and momentum, either coming into the interaction or leaving it. They're literally the X marks the spot on our map, telling us exactly where and how the strings are supposed to act.
So let's just walk through the whole process. Step 1, you pick your stage. For open strings, that's a disk. Step 2, you place your actors by adding those vertex operators right onto the boundary. Step 3, this is the heavy lifting. You do a very complex calculation called a path integral, which basically sums up every single possible way the interaction could happen. And finally, step 4, out pops the answer, the scattering amplitude, which tells you the probability of that specific outcome. Now, when physicists first ran through this calculation for the simplest possible case, just 4 open strings interacting, they found something completely incredible. I mean, you can imagine, after pages and pages of really complex math, of path integrals and all this abstract stuff, the final answer boiled down to something so compact, so unbelievably elegant, it felt like it had to be right. It was like finding a secret message from the universe. And here it is. This is the Veneziano amplitude. It was actually discovered by Gabriele Veneziano back in 1968, before string theory was even really a thing. And this beautiful little equation, written with this classic math function called the gamma function, it just perfectly described the data physicists were getting from particle colliders. It just worked. You can just imagine the feeling in the physics community. It was pure astonishment. How could one single formula contain so much information? This wasn't just about matching one little experiment. This equation seemed to hold some kind of deeper truth about how all particles behave. So what was the secret sauce? What made this formula so magical? Well, if you look at these diagrams, they show different ways particles can scatter off each other. Normally, you'd need a totally separate, really complicated calculation for each one. But the Veneziano amplitude brilliantly packaged all of them, all 3 possibilities, into one single elegant equation. This incredible property, where completely different processes are revealed to be just 2 sides of the same coin. That's called duality, and it is a cornerstone of string theory.
The discovery of this amplitude wasn't just a successful calculation, it was the moment that string theory went from being a whisper to a song.
So let's just take a second to appreciate the impact here. This was the first real calculable result to ever come out of the theory. It gave us this amazing unified picture of particle interactions. And maybe most importantly, it proved that string theory wasn't just some mathematical fantasy. It had real predictive power. This discovery basically kickstarted the entire first string theory revolution. You know, in physics, when a mathematical structure turns out to be this consistent, this elegant, and it unifies ideas that you thought were totally separate, physicists really take notice. It's almost always a sign that you're on the right track, that you've accidentally stumbled upon a much deeper layer of reality. And really, that's the thought that keeps thousands of physicists up at night, still working on this stuff today. The Veneziano amplitude was just the very first note in what might be a much larger cosmic symphony. It showed us the sheer power and beauty of thinking about particles not as points, but as strings. And it leaves all of us wondering, what other profound secrets are just waiting to be uncovered?